Hi, scientists. This is Mrs. Greenwald here, and today we're going to talk about the second part of Lesson 5. This is your follow-up assignment for the week of January 4th through January 10th. And at this point in time, you should have already either attended your live lesson and watched the demonstrations that were discussed in class, or watched the video recording of your teacher doing this assignment with you. You should also already have your notes in your book caught up. If they are not, you must stop this video, go back, watch that recording again, catch up your notes prior to doing this assignment, because this is a follow-up. This is intended to be done after that live lesson, and you should already have certain things in place before we move forward. Okay. So to complete this lesson, you are going to need your blue workbook. You are also going to need your vocabulary packet, as well as a purple colored pencil and a brown colored pencil. So purple and brown. If you do not have any of those things, please pause now, gather your supplies, get yourself in a quiet, comfortable, focused space, and then press play. Okay, let's begin. Again, this is Lesson 5, Part 2. We're trying to answer the question, how does water change state from solid to liquid and then to gas? How does it go from one state to another? And then how does this affect the water system? Remember, the water system being the water cycle, as well as all of the different components that we've been talking about: groundwater, runoff, infiltration, precipitation, etc. Okay. What I would like for you to do is, in your workbook, you have a space to jot some notes. What we're going to do is we're going to revisit that PhET simulator. And this time we're going to practice using those tools that we had asked you to not use last time. So we need to open the PhET simulation. And it says to select, once you get it started, it says to select the states button. And under atoms and molecules, so states, and under atoms and molecules, select water. Okay. So it says investigate state changes adding thermal energy. Well, when you think about the word thermal, I want you to think about what other words use thermal. Thermal blankets, thermometers. What does thermal mean? Well, thermal means heat. So when we're talking about thermal energy, we're talking about adding heat energy. In fact, what I'd like for you to do in your workbook, where it says adding thermal energy, I'd like for you to write heat. Okay. It says to start with water in the solid phase, and using the slider, heat the water until the thermometer reads between 330K to 365K. K is the Kelvin scale. We sometimes use the Kelvin scale in science, which is different from Celsius and Fahrenheit. So it might be one you're not as familiar with. Okay. It says you're adding thermal energy, you're adding heat energy to the system. Describe how the motion and relative spacing of the particles change when they gain thermal energy. Again, heat energy. So in the sim, what we want to do is heat the water until the thermometer reads between 330. We want to heat the water like that. See how it's changing at the time? We want to heat it to 330 to 365. 330 to 365. There's 35. What do you guys notice is happening? Go up a little bit more. My max is 365. Okay. What did you notice to that? What did that water do? It says to describe the motion and relative spacing of the particles. While we added thermal or heat energy, notice the water particles are moving more quickly than when they were a solid. Notice they're kind of spinning around and moving more quickly. They are still touching, but they're slipping and sliding past one another. Some of them are kind of branching off, but for the most part, they are still slipping and sliding. Now, what does that sound like to you? What state of matter does that sound like that we've heard of before? Okay, so describe the motion and relative spacing of the particles. So after adding thermal or heat energy, the particles are moving more quickly than when they were a solid. They are still touching and sliding past one another. Okay. Now I asked you to think about what does that sound like? They're moving more quickly than when they're in a solid state. They're slipping and sliding past one another. What does that sound like to you? Well, hopefully you said liquid. So we went from a solid to a liquid. What state of matter is the water in now? It's in the liquid state. Okay. What process did we just model going from solid to a liquid? That's right, melting. Solid to a liquid is the process of melting. All right. If you need to pause, please do. Make sure that you write all of this down before moving forward. Now it says to continue adding thermal energy to the system by heating the water until the thermometer reads between 800K and 825K. Now we need to describe the motion and relative spacing when we added more thermal energy to the liquid. Okay, so 800K, 800K is what we're looking for, so we're going to heat it. Notice what's happening to our molecules. We're looking for 825. Okay, 812. About 825 right there. Okay. Now, what do we see the molecules doing? Well, they're much faster, much more spread out, bumbling off of one another, but barely touching. Okay, so we've gone through another phase change. Let's talk about this a little bit. Okay. After adding thermal energy, so after we heated it, the water particles are moving much more quickly and are no longer touching. They are spread out. What state of matter is this in now? Hopefully you wrote a gas. And what process did we just model? Well, we went from a liquid to a gas. What process is that? Evaporation. And again, pause this if you need to catch up, if I'm going too fast. All right, let's continue on to part 2 of the investigation. This is losing thermal energy. Well, if we were gaining thermal energy and that meant heating, losing thermal energy, that's right, that means cooling. Okay. All right, it says to reset the water to a gas phase, use the slider to cool until the thermometer reads between 330 and 365. You are removing the thermal energy from the system. Describe how the motion and relative spacing of particles changes when they lose thermal energy. Okay, so we want to reset it to a gas. And we want to cool it until it's about 330 to 365. So cooling it to 330, 365. Okay, about in here. Let's get down to 330. All right, what do you notice the particles are doing? There we go, 330. They're much closer together. They're much slower. They're slipping and sliding past one another. What does it sound like? What, as we describe this, what phase change does that sound like? Now it sounds like we've changed it to a liquid. The water is now a liquid. So after removing thermal energy, so again, cooling it, the particles slowed down and began sticking together. They slide past each other. Okay, what state of matter is this water in now? Well, now it's in a liquid state. What process did we just model? Well, we went from a gas to a liquid equals condensation. Okay. Again, pause if you need to slow down and catch up. We're going to move forward, continuing removing thermal energy by cooling the system till the thermometer reads between 5 and 20 K. Describe the motion and relative spacing of the particles when they lose thermal energy. Again, when we're cooling it, losing thermal energy. So 5 and 20 K is what we're looking for. We're going to cool it down. Notice what the particles are doing. Whoops, sorry, I heated it up a little bit. There we go. All right, notice, look at these guys. They're much, much slower. They've formed a kind of a solid shape. They are really close together. They are still wiggling and vibrating, but in place. They're not slipping and sliding past one another anymore. So after removing thermal energy, or cooling, and the particles slowed way down. They locked themselves into place and are only vibrating in place now. Again, what does that sound like? Describing it this way, that sounds like the state of matter of solid. What process did we just model when we went from a liquid to a solid, which is what? Right on, freezing. Okay. All right. So, and the next thing that we need to do, and again, pause this if you need to catch up. Okay, so it's based on what you observed from the PhET simulation. How did adding thermal energy to the system cause the water particles to change motion and spacing? Think about that. When we added thermal energy, we heated it, we caused the molecules to do what? Well, they sped up and spread apart. We went from a solid to a liquid and a liquid to a gas when we added thermal energy. When we removed thermal energy, meaning cooling it down, the particles did the exact opposite. They moved closer together and they slowed down. They had little lower amounts of energy. And when these phase changes occur, they occur at different temperatures. So we're adding heat to get to a certain phase, and then we add more heat to get to another phase. Same thing when we're removing the heat or the thermal energy. We're going from a gas to a liquid, and then again, we remove more heat in a liquid to a solid. Notice adding thermal energy caused the phase changes of melting and evaporation, going from a solid to a liquid and a liquid to a gas. Cooling caused condensation and freezing, going from a gas to a liquid and a liquid to a solid. So they're exact opposites of each other. So think about condensation. This is the process of water turning from a gas into a liquid. So water vapor in the air cools and condenses. We see this in a variety of examples. We see this just about every day in clouds. Okay, water vapor cools and condenses into little teeny tiny liquid water droplets, forming the clouds. If you're a glasses wearer, you might notice this when you come in from the cold outside. Your glasses fog up, or from wearing a mask, your glasses are fogging up. What's happening is the water vapor in the air is touching your cool glass, the lens in your glasses, and it's cooling that water enough that it's causing it to form little teeny tiny water droplets. Condensation happens on hot days as well. Maybe you have a cold pop or a glass of lemonade. You notice the outside of your water glass is wet. It's not because your glass is leaking, but instead it's the cold glass, the water vapor in the air touches that cold glass, it cools, and the water vapor condenses or turns from a gas into a liquid. I want you to please make sure that you have out your vocabulary packet. Find the word condensation. Please put this in your own words. I also want you to record an example of what condensation is and when it happens. Think about all the examples I just mentioned. And don't forget to make sure that your drawing describes this process of condensation. I strongly encourage you to show on the molecular level what's happening, on the particle level what's happening with condensation going from a gas to a liquid. How are those particles changing? Pause this, and then when you are ready to move on to the next word, press play again. Okay. Thermal energy. So thermal means heat. Okay. When we're talking about thermal blankets, thermometers, a thermos, a thermostat, all of those things have to do with heat energy. So thermal energy is the total amount of energy carried in a system's molecules. We can add thermal energy. We can add heat to a system. We can remove heat from a system, heating and cooling. Again, please come up with an example in your own words, a definition in your own words. Pause this now. Be ready to move on when you press play again. All right. Please flip now to page 33 in your workbook. What we're going to do is add arrows between the different phases to show the direction. We have, we're going to do cooling phases, phase changes on the top, and then the heating phase changes on the bottom. Okay, so again, yours should already, you should already kind of look like mine. You've done this in a previous lesson with your science teacher. Okay, so let's start with going from a gas to a liquid. What are we doing? Well, we are, from a gas to a liquid, we are removing that thermal energy. What we want to do is draw a big arrow showing that that can be a phase change. We are removing the thermal energy. This is called what? Condensation. We are going to have to write kind of small to make that happen. Okay. In condensation, the water molecules lost thermal energy. So lose thermal energy, they cool down. I want you to write cooling in parentheses as well. Maybe up here, because it's also going to be in this phase as well. Cooling. All right, going from a liquid to a solid. Nice big fat arrow showing that we're going from a liquid to a solid. When we move from a liquid to a solid, what do we call this? This is freezing. Okay, the water molecules lost thermal energy. Notice condensation, freezing, those definitions are very similar. Well, not definition, but the explanation of what's happening, because we are in a cooling phase change. Cooling phase changes are condensation and freezing. The water molecules lost thermal energy. Okay, now down here, going from a solid to a liquid, what do we call this when we're going from a solid to a liquid? I wrote so big, I'm going to kind of have to do it down here. You might have room to do it right here. Okay. Solid to a liquid. This is called melting. And the water molecules blank thermal energy. Well, if they lost it up here in a cooling phase, what are they doing in a heating phase? They gain thermal energy. Okay. And liquid to a gas. Liquid changing into a gas. This is evaporation. Water molecules blank thermal energy. That's right. They gain it. Easy peasy. Okay, so notice that the cooling phases both lose thermal energy. The heating phase changes both gain thermal energy. Okay. So thinking back to our gotta have checklist, I want you to think about these questions. How particles gain or lose thermal energy causes their spacing of motion to change. Again, as they are gaining thermal energy, they're spreading out, speeding up. As they're losing thermal energy, they're moving closer together and slowing down. I want you to think about how the changes in particle spacing of motion causes the change in state. So as those particles are changing, it's causing the water particles to change from solid to liquid, liquid to gas, gas to liquid, liquid to solid. And then I want you also to think about how state changes affect the way the water moves in the water system. Okay. Water as a solid changing into a liquid, we call that melting. That's going to move a little bit more differently than would water vapor cooling and condensing in the cloud. So you want you to kind of think about where you might find that in the lot, in our lot models, in our examples. Okay, so at this point, those are the things that we should be doing, should know at this point in the lesson. If you don't know those things yet, you want to consider reviewing, going back to your previous lessons and trying to figure that out. However, at this point in time, we're going to try to answer our lesson question. We do this in the summary table, as you know, and the summary table for this lesson is on page 42. So make sure that you're flipped there to 42. And I'm trying to find 42. Sorry. All right, I have this written down somewhere. Sorry. Okay. Forgive me, I can't remember which book I did it in, but I do already have this written down. You should also already have B written down. I just can't remember which book I put it in. So at this point, if you don't have B already written down, please make sure that you go back and do that. For our purposes, though, I'm just going to jump ahead to part C. Okay? So it says my answer to the lesson question. Well, remember the lesson question is this at the top. How does water change state from solid to a liquid to a gas? And then the second part to that question is how does this affect the water system? Okay. Make sure you can see this. We're going to have to write pretty small for this. How does water change from state from solid to liquid to gas? Well, when we add thermal energy, when we add that heat energy to the water molecules, it causes the molecules to move faster and get farther apart. Okay. When our thermal energy increased enough for the molecules to move more freely and fast enough to evaporate, we have another phase change. So the more heat we added, the more phase changes we went from solid to liquid and then liquid into gas. Okay. Um, we know that gases move more freely. They fill the whole entire container. These particles spread out, they speed up, and they're going to fill the whole entire container. But what happens, and what happened in our demonstration, is that when the gas particles were closer to the edge of the cool bottle, the cool container, they started losing that thermal energy. And when they lose the thermal energy, they start changing back into a liquid. So they cool down, they get closer together, they slow down their temperature, and they start forming these water droplets. So the water vapor cooled when it got near the edges of the container and condensed into a liquid. Okay, formed water droplets, forming liquid water droplets on the bottle. The only way this could happen again is if those gas molecules start slowing down, getting closer together, losing their thermal energy. Okay. And then when gas molecules lose their thermal energy, we know a gas to a liquid is condensation, and a liquid to a solid is freezing. I apologize. There's not very much room for all of these things. Okay. So again, if you need to pause, please make sure to do that before moving on to the next part. Okay. What we're going to do now is we're going to flip back to our summary tables, our lot models. And let's take a look at the forest lot model first. This is again where you're going to need those extra colored pencils. You're going to need purple or a violet, maybe a dark pink, whatever you have available, and a brown. Okay, so we discussed pretty heavily the energy driver of gravity that causes runoff, precipitation, infiltration, and groundwater movement. And then the energy driver of sunlight. So far, we've talked about transpiration and evaporation, going from a gas to a liquid. Oh my goodness, I'm so sorry, guys. Absolute opposite of that, liquid to a gas. Forgive me. Liquid to a gas. Evaporation, transpiration are both liquid to a gas. Okay. Now we're going to add the two ones that we literally just talked about, condensation and melting. What is condensation? This is gas to a liquid. And then melting is solid to a liquid. Okay. All right. So condensation, we're going to mark as purple. And then melting we'll do as brown. Okay. So melting, we really only see this in a very small spot on our model. Now, again, this small spot really represents like a whole season change. Whenever we have snow melting, going from solid to a liquid, we see that. But in our model, it really is, it's just like the apples in the grocery store. We don't want to clog our whole entire model trying to show snow melting. So we just have it kind of in this one little spot. This one little spot represents, actually, I'm going to do a little straight arrow here. This one little spot represents really like every seasonal change, every time we have snow melting, solid snow melting into a liquid. Okay. And condensation. Now, what's tricky about this, what's going to be hard to kind of represent this, is we're talking about when water as a gas condenses and forms these clouds. Okay, it forms liquid water. It might form liquid water at or near the surface, but it's also going to form liquid water at the clouds. So it's from the gas. So what I'm going to do to represent this is I'm going to show a squiggly line going from a gas forming the clouds. This is happening from transpiration. This is also happening from evaporation. Okay. All right. So, and to represent this, I'm going to just kind of remind myself that they form clouds. All right. What I want you to do now is do this exact same thing to your present day lot model. So add condensation, gas to a liquid, melting, solid to a liquid, add what we just did to transpiration, evaporation, liquid to gas, liquid to gas. Add the arrows in the appropriate colors to your model. Make sure that they are in your present day lot model. Press pause. When you are finished, we're going to move on. All right. So at this point now, you've already added to your summary or to your forested lot model and your present day lot model. You may not skip that. You must keep it, keep your present day lot model as completed as your other lot model. Your teacher is going to grade these, look through and collect your workbooks when we return back to in-person learning. So make sure that you have what you need filled out. All right, I want you to flip back to that summary table again. And funny enough, I found it. I just put it under the wrong lesson. I'm sure you've done that before. I found B, but I put it in the wrong lesson. That's why I couldn't find it. If you do that, just make sure that you maybe cover it with paper and write over it, or label it somehow so you don't get it mixed up. But I found it under lesson 4, so just make sure if you do something like that, that you have a way of correcting it. Okay. So it's asking us to connect our ideas to the unit challenge. Before we do, I want you kind of thinking about what would happen if to the water cycle. What would happen to the water cycle if water no longer could change state? If something happened, water could no longer change state, what would happen? Would water still move from one reservoir to the next? Well, the answer is no. If we did not have the water cycle, if we were not able to move water from one state to another, we would not have any sort of movement from either from the stream to the air, or from the clouds down to the stream from groundwater movement. Like once the groundwater was gone, it would be gone forever because we wouldn't have this constant cycling of water. Okay. So the question that we now have to ask for part D, tying this into our whole entire unit challenge, trying to figure out what's happening to the water in the stream and what can we do to fix it. How did converting part of the forest to a parking lot influence the way that the water changes state? Think about when we changed that forest, how did it affect when water changes state? Well, the sun adds energy to the system, which increases the thermal energy of the surface water. Okay, so the sun adds energy, it heats up the system, so it's increasing the thermal energy, meaning the molecules are moving faster. When thermal energy is increased enough, the molecules move more freely, fast enough to change state. This can cause snow and ice to melt or surface water to evaporate. When less energy from the sun is being added to the system, the thermal energy decreases. This means that molecules move slower. We have different phase changes. Thermal energy is decreasing enough, the molecules move slow enough to change state. And this can cause water vapor to condense and for liquid to freeze. These states change how the water moves through the water system. So when we are changing what we have going on, we had a lot of transpiration, a lot of evaporation happening in the forested lot model. We have less of that and more runoff. We have more liquid water. It's not able to change those states as easily, which is why you have that pileup. I know I talked to my kids about the runoff kind of filling the bucket. It would be like taking a hose and directly filling a bucket into the stream. And even if that bucket had little tiny holes drilled in the side, just like a stream bed has the possibility of infiltration back into the groundwater, it's not moving fast enough, which is why you end up having that overflow. So we know that sunlight adds thermal energy, causing molecules speed up and spread out. So this is changing, phase changes. These are adding thermal energy phase changes. This is melting and evaporation. And then with less sunlight or thermal energy, molecules slow down and move closer, which is the phase changes of condensation and freezing. All right. And so when we are changing what's available for the water to move through the different parts, like less transpiration, less evaporation, then we're changing how that water is moving through the system. Okay. All right, ladies and gentlemen, scientists, this is what we have for today's lesson. Please make sure that you have this fully completed, because when we return to our hybrid setting, in school setting, your science teacher is going to collect your science workbook and make sure that you've been doing what you've been needing to be doing since Thanksgiving. We've filled out our workbook quite a bit. If you've been following along, you're probably good to go. If you have not been coming to class or not watching the follow-up videos, you're going to have a lot of work that you need to catch up before your teacher takes a look at your book. So please take some time, make sure that you're flipping through, you have everything filled out properly. Please make sure that you're going through that gotta have checklist, that you understand what we've been talking about so far, and that you're all caught up so we can have a nice fresh start when we return to our in-person learning on the week of the 11th. All right. Bye for now, scientists. As always, stay curious.